Thank you. Okay, there we go. My name is Larry Lassard, and I'm from Achieve Renewable Energy, and I'll be presenting information about ground source heat pump. My company has installed about 350, 375 ground source heat pumps in 150 or 200 separate projects. We do both residential and commercial installations, and I'm a certified geo-exchange designer, which is the highest level of certification for us geo guys that's available in the US. When they had us work on this slide, they asked for an interesting fact, and I noticed that all the other speakers I watched today didn't put one in, so I got sucked in. But it's okay, I made mine up. Actually not, but that's fine. So our objectives today are to help you understand how ground source heat pumps fit into the Massachusetts environment and give an initial inclination as to what best practices are for design. Importantly, talk about the rebates and incentives for ground source heat pump, which are actually quite tremendous here in Massachusetts. And then give a summary of some items to think about in evaluating ground source heat pump for a new design. And the overarching goal is to enable the design and construction community to have an understanding of when they can select ground source heat pump as the appropriate option. So the first thing about ground source heat pump that you should understand is you don't need a volcano. There were some great TV shows on Discovery and the Science Channel back when they actually had things about science on those channels instead of things about moonshine and fixing cars. And they all focused on Reykjavik, Iceland, and high temperature water being used directly for heating, and that's not what we do. Our work with ground source heat pumps ends up having several names, three of which I guess are polite. One being what the clients call it, which is geothermal. That's what they understand it to be. Usually, though, they'll spell it GEO and then a space and a capital T. And as a geologist, that bothers me, but I try not to say anything because they're prospective clients. But also talking about the technologies, ground source heat pump and geo-exchange, those are all accurate descriptors. And the ground source heat pump devices we use move heat to and from the structure to provide either heating or cooling. And because the heat pump is not creating the heat, but instead moving it from one location to the other, the efficiency of operation can be much higher than with a conventional or fossil fuel system. In the wintertime, when it's cold outside, the ground source heat pump doesn't have any consideration for what the outside temperature is because it's not exchanging with that outside environment. It's exchanging with the ground, which in our area starts somewhere between 50 and 55 degrees at the beginning of the season. Depending on the ground source option that's selected, that temperature might fluctuate over a heating or a cooling season. But at any rate, the exchange is with a temperature that's much more moderate than the outside air. So that's why the ground source heat pump efficiencies are a multiple of the air source heat pump efficiencies. In the summer, the heat flow through the equipment can be reversed. So heat from the building is pumped into the ground, which again will accept that heat more readily than the outside air will because the temperature in the ground is more moderate. This is a cool slide, but it takes a little explanation. So let me put my glasses on, turn around, and try to work through it with the pointer. Heating systems are rated based on the coefficient of performance, COP. And that's a simple ratio of the amount of useful energy you get out divided by what you put in. If you consider for a moment an electric hot water heater or electric resistance heat, if you put a kilowatt of energy into that electric element, a kilowatt of electrical energy into that element, you'll get a kilowatt of thermal energy. So the COP would be 1 or the efficiency would be 100%. With a fossil fuel system, a portion of the energy always goes up the flue no matter how efficient that system is. So the COP of a fossil fuel system is always less than 1. In the case even of a very efficient fuel oil system, it might be 0.87. Older fuel oil systems could have a COP 0.7 or 0.8. Same for gas or propane systems. A heat pump, especially a geothermal heat pump, the energy you put in is being used to harvest energy from the ground during the heating cycle. So because your only overhead is the harvesting of that heat, you always end up with more heat put into the structure than energy you put into the system. So our COPs are always a lot larger than 1. Ground source heat pumps can vary based on model line and particular configuration, but the COP is typically between 3.5 or 350% efficiency and about 6 or 600% efficiency, so somewhere in that range. The Pac-Man type diagrams on the bottom are meant to show 2 things. One is that you lose some of the heat with a fossil fuel system, and then also the size of the pie charts are proportional to how many BTUs you get per dollar that you spend. So with electric resistance, you get the lowest number of BTUs per dollar because electric rates are high and your COP is only 1. The fossil fuel options are somewhere in the middle, and then heat pump doing geothermal exchange has the greatest number of BTUs per dollar spent. Installation costs for geothermal systems on the top line is much more expensive than the other alternatives, because we have to do all the underground stuff that I'll describe in a few minutes. But so with only this graph, you'd wonder how I made a living doing this stuff. But there are tremendous financial incentives both on the state and federal level. So the post-incentive install cost for geothermal is in the same range as the other alternatives. And some of the other alternatives, like natural gas, can sometimes be more expensive than the average if you have to bring a gas line into the structure, and depending on how far away that gas line is, that can cost thousands of dollars. This is also a very illustrative chart, and I'll try to walk through it. We have on the x-axis here, we have the different technologies. And then for the tan or brown bars, we have total operating cost over a 20-year period. And for the slate-colored bars, we have tons of carbon dioxide that are emitted by that same system over that same 20 years. So electricity has the highest operating cost. I think we all know that. Oil's a little bit better on operating costs, but nearly as bad on carbon footprint. Natural gas has a very low operating cost, but a decent carbon footprint as a result of burning that fuel. And geothermal has an operating cost that right here is shown to be almost identical to natural gas. It's actually usually a little bit lower, and then a very low carbon footprint because of the efficiency. And that greenhouse gas intensity will be improving over time. The grid in Massachusetts is getting more and more green with installation of solar and wind and offshore wind. So over time, the electrified heating options will have lower and lower carbon footprints. There are economies of scales with geothermal installations on the residential side. This is primarily because ground source heat pumps are expensive compared to other heating devices. And if you're going to heat a house, you need at least one. And that first heat pump costs you a chunk of money. If it's the smallest size in its model line, you're still paying a decent amount of money for that heat pump. But then jumping up sizes, say from a 2 to a 3 to a 4 or even up to a 6-ton capacity unit, those changes in capacity have only small incremental changes in cost. So it's absolutely not the case that a 3-ton heat pump costs half as much as a 6-ton heat pump. It probably costs 85% the cost of a larger unit. So in larger homes, up to the point where we have to put in a second heat pump, the cost per square foot for our install goes down. Then then the cycle starts again if there needs to be a second heat pump because the house is larger. But that having been said, even in a small house, if it's very efficient, the ground source install can be relatively inexpensive and have very low operating costs, and it pairs very well, as we'll discuss in a few minutes, with technologies like solar PV. The incentives in Massachusetts are very good. I will spend, when I'm meeting with a prospective client, almost as much time talking about incentives as I do the actual details of how an installation would happen, because while the incentives in Massachusetts are very good, they come from a variety of different sources, and that adds a little bit of complexity. So running down from the top, the Department of Energy Resources has an alternative energy credit program. You earn these alternative energy credits based on the amount of thermal energy the residential system, or commercial in this case, but we're talking about residential today, that the residential system would generate over a 10-year period. Unlike the old SREC program for PV, the AECs on a residential program are available all at once. So you have one transaction close in time to when the system was commissioned, and that helps very much with offsetting the install costs in the short term. That amounts to, they have a calculator which roughly calculates to about $2.50 per square foot of the residence is the value of the incentive. That's for an existing home that has a HERS index greater than 50. In a couple of slides, we'll talk about what happens if you're below 50. The Clean Energy Center has a rebate that is based on the size of the system that's installed and provides up to $10,000 to anyone, and based on certain income adders can get up to $17,500. That program has limited funding and right now is anticipated to be fully subscribed by about February. But at least for now, that's available. And the program is run based on date of your application. So you don't need to have an install finished by February, or whenever the shutdown of the program happens. You need an approved application by that time. MassSave has a program for new construction that ICF can tell you more about. MassSave also is transitioning their incentives based on the value of fuel switching to reduce carbon. So there'll be more in the way of ground source incentives from MassSave at some point soon. IRS provides currently a 30% federal tax credit that is scheduled to go to 26 and then 22% in the next couple of years and then be phased out. About 6 weeks ago, our national trade organization that's linked up with the solar PV trade organization was very confident that that was going to be extended at 30% for 5 years and wasn't going to go down. And then every day is tax-free weekend for geothermal systems in Massachusetts. They're sales tax exempt for residential systems. Ground source heat pumps pair very well with both solar technologies. This slide shows solar photovoltaic modules here for generating electricity and solar thermal modules here. The PV is the most straightforward. If you're switching to an efficient electric-based heating system like geothermal, you put up PV, you're going to offset the electric use directly and can get to net zero through that approach. Solar thermal or solar hot water systems can be used for hot water in conjunction with the geothermal system. It's also possible to dump heat from the solar thermal system into the geothermal ground source and store it there for winter use. Both technologies, both solar and geothermal technologies, improve your HERS score. And as I alluded a minute ago, that we're going to talk about how that affects the incentives. PV costs have come way down in Massachusetts. So at one time, clients used to have to decide, do they want to put in PV or do they want to put in Geo? And now they can more easily decide to do both. All right, this chart talks about different scenarios interfacing a ground source system with a PV system. In the first column, powering the system through the grid. So for an average type house, there's no additional cost because beyond the geothermal install, because you're not putting in solar. And in the model that was run here, the heating of that average home with the geothermal system was around $1,050 for the year. And in a new construction scenario, that would be lower because the new construction would be a tighter home. In that average home, to offset the operation of the ground source system, you need about 4.3 kilowatts of solar array, which at current rates is about $17,000. But you get the tax credit, you get payments based on the electrical generation, and assuming your HERS score is greater than 50 still, you have about a $7,300 net cost for adding the solar, which means about just under 7 years for payback of adding solar, and then you're at a point where there's no fuel cost at the house. In the more efficient home, you have a smaller array, which has lower net cost, and then it's most likely that you would then have a HERS rating that is less than 50, and the AEC program uses multipliers based on the thermal energy to calculate how many AECs you get. So if you have a residence that's greater than 50 on the HERS score, the multiplier is 5. For every megawatt hour of thermal energy, you get 5 AECs. If you're below 50, the multiplier becomes 7, resulting in more AECs and more income from that program. And in that case, the payback for having put in the solar is under 3 years, about 2.5 years. If you can get below the 50 HERS rating, you get about an additional $1 a square foot out of the AEC program. And both PV and Geo reduce HERS scores, and a code-built home would probably have its HERS score already in the 50s somewhere. So with both technologies, you'd almost certainly be below 50 for your score. And that has an impact on operating cost. So here we have system net cost in the orange-ish tone, the adder for PV for offsetting the power usage, and then total operating costs, so in the red bar, the fuel usage by the conventional technologies. So for a little bit more than that already competitive amount that we talked about, about 10 slides ago, you can get to a zero operating cost. All right, the geothermal equipment. So ground source heat pump systems are relatively simple on a conceptual level. You need the ground source heat pump itself, which is shown in this cartoon, has some heat exchangers and a refrigeration compressor and a blower in the case of a ducted system. You have the ground loop, or the ground heat exchanger, and a distribution system, which in this cartoon is a ducted system, but it could just as easily be hydronics. And then the controls are where things get fancy, where we can start doing zoning and internet connectivity and monitoring and all that stuff. and we'll talk about that in a little while. In life, form usually follows function, so the equipment that replaces a residential furnace looks kind of like a residential furnace. And the equipment that replaces a boiler looks kind of like a boiler. This is a water furnace variable speed heat pump, and this is what they like to call a packaged unit, meaning all the geothermal stuff or all the ground source heat pump stuff is down in this bottom compartment, and the air handler is in this upper compartment. So the ground source heat pump and the air handler are packaged together, and hence they call it a package unit. They are available in a split configuration where you'd have the geothermal units in a mechanical space and then refrigeration lines connecting to a remote air handler. The boiler replacement units simply heat or chill water to meet a hydronic demand. This is what the outdoor equipment with a geothermal system looks like. It's obviously been a while since the install because the grass all grew back, because we do make a little bit of a mess when we're doing the install. But there is no outside equipment, so you don't have air conditioning condenser outside, you don't have air source heat pump outdoor units that are mounted on the home, all of that's missing. So if we go to a home to do a retrofit and they don't have air conditioning, then we want to take a before and after photo, we can just use the same photo because the house will look the same when we're done, which has always been kind of a bummer because when the PV guys show up, you know, they put the thing on the roof and there's this big badge of greenness. And when we do our work after the landscaping's restored, you don't know that we've been there. So the clients like that, but you don't get any free advertising out of that. Ground source installs, the ground heat exchangers are always constructed of high-density polyethylene piping, specially selected for geothermal based on their thermal properties, chemical resistance, and the mix of rigidity and flexibility. The piping is joined with a heat fusion process. There are no mechanical connections, so you're not screwing anything together. There are no wrenches. Everything is melted together, and it's a very reliable, long-lived technology for piping. When you see them putting in the gas lines on the street, that's the same high-density polyethylene pipe. It just happens to have a yellow jacket on the outside to identify it as gas, and that's all thermally welded, just like our stuff. The pipe typically comes with a 50-year warranty. That's a warranty for the pipe, so if it leaks, they give you a new piece of pipe. Water furnace provides, at a limited additional cost, but they provide a 55-year no-leak warranty, and they'll replace the loop if there's a problem. Then distribution can be anything that you'd normally do in a home. Distribution by ducted systems is most common because we do heating and cooling that way. But it is possible to retrofit or install baseboard radiation. Typically, we try to put in baseboard that's designed for the lower fluid temperatures of the geothermal equipment. Other manufacturers, their equipment tops out at about 125 or 130 degrees Fahrenheit, which is not close to typical boiler temperature of 165 or 175. Water furnace has a product line that makes it up to 145, 150, so that's closer, but still lower than the boiler. But most of the installs end up being ducted systems because the heat pumps out of the box can make things warm or cold. And without ducting, you don't get the air conditioning. Unless you do something fancy like a chilled beam or something, but you're not going to do that in a house. Pairing with radiant floors is exceptionally efficient because the fluid temperatures are lower, so the COP on the water-to-water geothermal units can be very high because there's less of a temperature differential they have to account for. And then integrating with other modern technologies like mechanical ventilation or high-level filtration is easy with a geothermal system, at least a ducted one. You can't really put an ERV onto a hydronic system, of course, but with the ducted systems, it's quite easy to run the HRV and have an integrated set of controls for the two technologies. The standard filtration on most of the geothermal heat pumps is MERV 11 or 13, but they can be ordered with everything up through HEPA filtration. Domestic hot water. Unlike some of the other technologies, ground source can help with domestic hot water. There are two approaches. The simplest but most expensive is to have a separate ground source heat pump that's dedicated to providing 100% of the domestic hot water. Or if you have a hydronic load like radiant flooring, size the heat pump a little bit larger and have it automatically switch between domestic hot water and the radiant floor. And that can be relatively cost effective, but putting in the pumps, controls, and heat pump just for domestic hot water can cost some money. The more common way that it's done, which is somewhat harder to explain, is with a device that's unfortunately called a desuperheater, which is a name that no one understands what that means. Well, I shouldn't say no one, because I do, and some people in the audience may, but when we're talking to potential residential clients, none of them know what a desuperheater is. It sounds like anti-disestablishmentarianism, Superheat's a condition in a refrigeration circuit where describes the circuit having extra energy. And ground source heat pumps will develop that extra energy most of the time when they're operating. And the desuperheater is simply a heat exchanger, pumps, and controls that's used to shunt that extra energy over to a hot water tank. So the normal scenario would be with an electric or heat pump water heater tank, set the tank to maintain 120 degrees and tell the ground source heat pump to try to keep it at 130. And keeping it above the tank set point takes the load off that alternate water heating system. Now, this all happens as a byproduct of operation when the equipment's operating. So on a very cold day or a very hot day, the hot water assist could be up to 100% of the hot water demand for the house. But on a day like yesterday, or I haven't been outside since 9 o'clock, but I assume it's nice out there again today. On a nice day when you're not running the HVAC equipment, there's no byproduct of operation if there's no operation. So in this scenario, you need a domestic hot water system that can meet all the needs of the residents, and then the geothermal system will just make it more efficient when the geothermal system is operating. There are a number of ways that performance is ensured. The controls for a ground source heat pump system can be quite sophisticated because one ground source heat pump, especially the water furnace equipment, can modulate its output in a way that a conventional system can't. So one ground source heat pump can support multiple temperature zones. In the case of the variable speed water furnace equipment, up to 6 temperature zones off one machine, providing that you can make all the ducting runs to also support those zones, which normally you can in new construction. If you're starting from scratch with putting in ducting in a existing home as a retrofit, you might be limited in how many zones you can have just because the ducting can't be in concealed areas because those are already finished. But at any rate, the controls will control the temperature, of course, and then can control humidity, both humidifying and dehumidifying, and have the various zones. The water furnace equipment, and soon some of the equipment from other manufacturers, is instrumented. And it has all the information of how much electricity is being used, what the demand call for the unit was, the refrigeration pressures and temperatures, the state of a whole bunch of different variables. And in the case of the water furnace equipment, about 100 variables get recorded every 10 seconds and stored. And if a client has an intermittent issue that they want us to investigate, with that kind of monitoring, we don't have to camp out at their place until the intermittent thing happens. They just have to tell us what day and what time it happened, and then we can access all the data and know as much about what was happening as we would have if we were there with all of our equipment hooked up to the machine. The client can also monitor their electric usage and historic electric usage, and the equipment issues trouble codes if there is a problem, and there are verbose messages that tell you essentially everything you need to know if you're a trained technician to understand what you need to do to address it. And because we can also make configuration changes to the equipment remotely, in something like 90% of the instances, we resolve things without leaving our desk. That is, there are other manufacturers that I think are trying to catch up. So I don't know anything about timeline, but I would imagine there'll be competition to that at some point. The water furnace controls have been in place for 5-6 years now, so we're pretty used to using them. The ground source, if it's a closed loop system, whether it's vertical or horizontal, has a very long life on the order of decades. Vertical closed loop in the type of rock we have, I see people estimating longevity between 100 and 300 years. So with the ground source, you're installing that, and that's your fuel for the foreseeable future. And the equipment inside may wear out over time, but the ground loop is reused. So if you have to do a life cycle replacement, it's just for the indoor stuff, not for the outdoor stuff, because buildings are expected to stay the same efficiency they are now or get better. If they were getting worse, then you'd maybe have to add more ground source, but that's unlikely to be happening unless there's an expansion of the building, but then you can handle that as as if it were new construction. The indoor equipment, ground source heat pumps, are estimated to last about 24 years on average, and that's about double the longevity of an air conditioning type system, and 50% to a third longer than a boiler or a furnace for a fossil fuel system. That's what ASHRAE estimates, right? And Water Furnace has been selling equipment for something more than 35 years, and I mean, a lot of the first stuff they sold is still in use. But that estimates are made by an industry group, not Water Furnace. There is some maintenance, primarily changing the air filters, but depending on the ground source, you might need to pay attention to minerals in the water coil if you have an open loop system, and the air coil might need to be cleaned on a regular basis. Circulating pumps and blower motors will last as long as they last, usually a pretty decent amount of time. And condensate drains need to be maintained because they get microbial growth in them and get clogged, so you need to annually look at the condensate drain, but that's the same as a requirement for any air conditioning system. All right, some considerations for new construction design. We normally get involved in projects at the very beginning and continue on through till completion of the project. The contractor or the homeowner may have questions and want to learn about geothermal, and we're there providing that support. Helping with the design, giving our opinions on things that could be done differently at the house so that we can put in a smaller system. And then we're constructing the system, which usually is spread over the construction of the home, where we do the drilling before the framing happens most often, but then don't install our equipment until the house is secure and weathertight. And then we're not really done commissioning the system until they're normally doing final painting. We're mounting the final thermostats and all of that. As I've mentioned, the HER score matters because it affects the alternative energy credit incentive, but both PV and Geo help get below that threshold of 50. In design of a system, it's not a good idea to just sort of dress up a poor performing house with a highly efficient heating system. You're somewhat robbing Peter to pay Paul in that case. If the house is more efficient, then we do less drilling, so the money saved in not insulating the house to the greatest degree possible, it ends up getting spent on us doing the drilling, so might as well do the insulation instead. And there are some factors relative to complexity and sizing. For a conventional system, fuel availability is important, whether it's availability of natural gas lines or requirements that might be in place for storage of fuel oil or propane. With ground source, we also, and those systems have to pay attention to what the heating load for the house is and the cooling load as well. And ground source similarly has to pay attention to that. Our systems are normally designed much closer to the actual heating load and cooling load than the conventional systems are, which are often largely oversized. But in addition, you have to think about what the geology is and need to be working with a designer that understands that so that the ground source can be appropriately designed. And the layout of the ground source matters as well relative to setbacks from property lines and septic systems, water supply wells, the areas where there might be a plan for future expansion or to put in an in-ground pool, all those places you need to think about and try to avoid so that the ground source isn't in the way. And normally there's a very reasonable solution that can be had. This diagram shows the plumbing for the most complicated piece of equipment water furnace has, which provides ducted heating and cooling and radiant flooring and contribution to domestic hot water. Usually the systems are simpler than this, and this one's not all that complicated. When you go into a mechanical room for a ground source heat pump system, it's my opinion that you shouldn't feel like you're going into a submarine. It shouldn't be piping everywhere and lots of complexity because the systems can be installed in a very simple and easily serviceable manner. So as I mentioned, a single geothermal unit can provide up to 6 zones. Normally, the residential equipment is in the range of 2 to 6 tons. Tons is a terrible unit of measure, but I can rant about that on my own time. And the radiant heating, domestic hot water assist is all possible, and then no fossil fuel use in the house is commonly achieved. Hydronic systems are a little bit more complicated. This is a relatively large hydronic system that has 5 or more heat pumps, and it's providing radiant flooring and domestic hot water, and there's a lot going on here. But even so, it's still a pretty compact install. This number of heat pumps would be a pretty large house, maybe 10, 12,000 square feet. You will see references in the literature to ground source heat pumps being used in a dual fuel configuration, where the ground source heat pump heats the structure to a certain point, and then a gas boiler or something takes over. I want to throw holy water on the computer when that sort of thing pops up, because there's no need to have any kind of backup source for a geothermal install. So dual fuel installations, when they're done, in my opinion, should only be done because there's an existing existing hydronic source, and it's easier to integrate it than throw it away. But our design goal is always to provide 100% heating and cooling. This is the bedrock geology map of Massachusetts. Any questions? Massachusetts has complicated geology. Over here, this used to be part of Africa. This is all glacial outwash from the last ice age. There's a sedimentary basin here. Continent, this has been all eroded by the Connecticut River. This is mountainous carbonate-type rocks that were thrust up in an orogeny. That's a geology term for when a mountain system is being built back in the Allegheny period, which was many, many moons ago. The point is that if you understand the geology, or at least can read the key to this map, you know things about how the design should be done. For instance, the rocks in this area and down here, and a lot of the Cape Cod are pretty high quality water. So an open loop system has a good chance of doing pretty well. Out here where the carbonate rocks are, you'd have harder water, alkaline water, and you'd have more mineral precipitation. Then in the sedimentary basin right around Boston, you can get some pretty poor water quality as well. So in trying to site an open loop heat exchanger, knowing the geology and then being able to look at the well drillers database for what's happened at other wells installed is very helpful. Also, the thermal conductivity of the rock is different. Thermal conductivity of the rocks up here is very high. Cape Cod's sands and gravels are kind of in the middle, and the rocks out here that are carbonate-type rocks are lower. So that all affects how much ground source you need to have under the particular conditions. On a commercial scale job, we would do a thermal conductivity test where we'd actually go out and measure the performance of the ground, but it's not cost effective to do that at a residence. So instead, we try to look at the rock types and equate the performance to other projects that we've had. Drilling is not a surgical technique. It's a little bit loud and it makes a mess. This is ground up rock that's come out as the bore was done, and then the grout material that goes into the boring. So this all has to get cleaned up and then re-landscaped. Horizontal loop systems are also possible, and you can do that by excavation, but you need a relatively large area. Normally, trenches for geothermal are about 3 feet. Depends on what piping configuration. You're going like this. So the slinky configuration, where the piping looks like a slinky that's been pushed out flat, would normally be 1 ton of capacity is a 3-foot by 100-foot trench. And those are 10 feet on center. So 4 tons of capacity would come out of 2 borings to 300 feet each, or 4 100-foot trenches 10 feet apart, so a 100 by 30-foot area, or actually more like 40 feet because the trenches have some width to them. Depth from the surface should be as deep as you can get it to be, because the soil temperature varies over the course of the year and it gets more stable at depth. So it should be at least 5 or 6 feet for a good design. But if we can put a horizontal system in where the excavation is 10 or 11 feet deep, that's more beneficial. Or if we can be a foot or 2 into groundwater, that's more beneficial. There are trench safety requirements for any excavation that deep. So then the slinky option that you were thinking of is helpful because that's assembled above grade and can be lowered into the hole. No one has to go into the excavation. But deeper is better. So the most common installation is a vertical closed loop. For a typical house, that would be 1 or 2 borings, so it takes about the space of a parking spot, and everything's finished below grade. And so you can have driveway over that, you can have building over that if you want, landscaping, whatever you want to do. Just don't put it someplace where you're going to want to dig for a pool or have to put a replacement septic system or something like that. And so it's very predictable in cost, but drilling is expensive in our area because that great thermal conductivity that we have in our rock also is because the rock's really hard and dense. So you need a bigger drill rig than you would use in other parts of the country. The other three alternatives are the horizontal closed loop, which we just talked about a little bit. You need a fair bit of space, and that can be less expensive than drilling unless the soil conditions aren't good. If you have a lot of material you have to dispose of and a lot of boulders or rocks that you encounter, the cost of a horizontal system can actually end up more than a vertical system. It's very common, and there's a lot of space required, so in urban areas, this just is usually a no-go. Open loop systems in our area are done with a standing column well configuration. Water is pumped out of the well, processed through the equipment, and then returned to the well, with the return point and the pump intake being at opposite ends of the well. And depending on a variety of factors, the pump would either be at the bottom or the top. You get a little bit more output out of the equipment with a standing column well because the fluid temperatures are higher than closed loop, but the pumping cost is higher too. So the overall efficiency between the two methodologies is pretty similar. And then in other parts of the country, pond loops are really popular. In fact, water furnaces' entire factory is heated and cooled off a loop that's in a pond in front of their place. In Massachusetts, the permitting is just crazy to try to do this for two reasons. One is Conservation Commission permitting, so you're not just digging in the buffer zone, you're actually digging into the pond. Because we transition to the pond, the piping has to be below frost line. And in Massachusetts, people typically don't own the pond, they own up to the frontage, and the pond's owned by the municipality, so now you're asking to put your ground source under some public body of water. And so it's just not so commonly done. More common in New Hampshire, it's based on local state regulations. All right, considerations during design. So when looking at the whole project, understanding the geology is important, knowing the local regulations, particularly the Board of Health regulations are important. There's wide variation town to town in what the Board of Health requires for permitting, and what some require engineered plans, other towns don't have permits at all. There's a wide variation, so you have to think about that at the beginning. Access for the drilling equipment or excavation equipment is important. And knowing accurately the heating and cooling loads is important. And when you're in the design phase, it's really important to do the heating and cooling load analysis based on what's really going to happen. All of our residential clients start out saying they're going to put closed cell spray foam everywhere. And then that, during construction, will frequently change because they want to spend money on better countertops, or wouldn't it be nice to get a pool table or something like that. And so there has to be commitment at the time of the design that this is what the insulation package is going to be, because we typically go in and do our drilling very early in the project, and you can end up with a ground heat exchanger that's too small because they made the house a little bit more crappy than they led you to believe. So design professionals, architects should try to keep that in mind. And if there's been a commitment to a particular insulation and window and door package, stick to it and cut corners someplace else, or don't have us start work until everything's really finally decided. And then there's a need to restore the landscape afterwards. In new construction, that's not really so much of a problem, but in a renovation, we make a mess. The clients have to be aware that drilling's going to tear up the lawn, and then but that it's okay. It can be repaired. We've had some clients go to tears because the grass got damaged. We've had other clients that have asked us to come do the drilling a particular week because they're going to be away, so make as much noise as we can. Distribution system. We can have any kind of distribution system that the client wants. But most commonly, architects put no allowance on the plans for HVAC whatsoever. And it's fair that they don't, because at the time they're drawing the plans, they don't know what the system's going to be. But the better practicing architects have a revision schedule built in that allows them to put in duct chases or things like that once decisions have been made. And so, architects in the audience, please do that. Please, make the clients understand that they eventually are going to need an HVAC system in this house, and that they might need to move the refrigerator by 18 inches to support that. And planning for how you're going to handle domestic hot water is important because it affects whether our system's going to interface with the domestic hot water and affects how we configure the equipment when we order it. Relative to the mechanical room, there are some advantages for ground source heat pump. The equipment's about the same size as conventional air handlers or boilers or furnaces and boilers, but we don't need any venting or fuel lines, so it can be central to the structure. It doesn't have to be on an outside wall. And since we have no combustion, there's not a requirement that that space have a particular rating for the wall and ceiling construction. We do need some space around the equipment for service. Typically 2 feet around the equipment is what we ask for, but that's the same as a conventional piece of equipment. When there's a perceived value to using the most efficient technology, and whether that's the homeowner being proud on their own or feeling like the contractor is looking out for them by offering the most effective solutions, or thankful that the architect brings up the various choices that they could consider. And all of that can lead to a home that's more comfortable and more valuable. It is. You need to be very careful to make sure that there aren't any leaks in that system. The vertical loops are normally almost fitting free. Even a 500-foot boring, there'll be a continuous piece of pipe going down to the bottom. Then there's one fitting that turns it around and comes back up to the surface. So it's unlikely that that's going to leak, especially since those U-bends are shipped from the factory pressurized. So when we are about to put it in, we cut them open. If it still has air pressure in it, that's the best of indications that things are fine, but then it gets pressure tested again after the install. But the individual fittings connecting to wherever your mechanical space are, you want to double check those because they're not accessible afterwards. Again, I can't remember the last time, I can't remember actually having had a failed fitting in the subsurface, but it's conceivable that would happen. It would be a shame if it was under the house. We prefer the loop to be outside of the building envelope if possible, but there's no reason not to put it under the house. It's just our general preference to have it outside if we can. Down and back up in the boring. The borings are 6 inches in diameter, and the piping inside diameter is 1.25 to 1.5 inches, depending on the design. And so that all goes down as one piece. No, they feed it down afterwards. They pull all the bits out and they feed it down. They have to do some things to support that. They have to fill it with water because otherwise it would be incredibly buoyant. And even so, it's still somewhat buoyant because the groundwater is more dense than the tap water that ends up in the system. But it goes down as one piece, and then a grout material is inserted from the bottom to the top. And the purpose of that grout is twofold. It stops any contaminants at the surface from making it down to depth to protect the aquifer, but then it's also designed to have a high thermal conductivity to help the interface with the rock. So the grout material that we use is made out of bentonite clay and graphite. The well casing gets sacrificed to the hole. So, and one thing I forgot to mention was relative drilling costs. People think, oh, you know, we often get these questions like, what if you hit rock, as if the drill rig can't go through rock. You know, that's what they're designed for. And they go through rock faster than they go through soil, because when they're going through soil, even though it's softer, they have to advance that casing as they go so that the hole doesn't continually collapse. And the drilling through soil and setting casing is almost twice as expensive as drilling through rock. So we like to hit rock almost as soon as possible. But, you know, the earth is how it is. They can tell when they're grouting, and there wouldn't necessarily be voids in the crystalline rock we have in eastern Mass, but the rock out in the western part of the state could have voids in it. In the eastern part of the state, it's more common that you'll hit an area that has large intersecting fractures, and they need to grout those fractures out a certain distance from the well. It's not something that gets measured, but it's something that they understand based on how quickly the grout's coming up, whether it's still leaking out into a fracture. And they, you know, so they'll want to make sure that's filled. Because the grout doesn't actually ever really harden. You know, it gets kind of hard, but it's still plastic. So with all the pressure of a couple hundred feet of that grout on the boring, if you're in a fracture zone and they haven't sealed it properly, the grout will run down. That'll happen almost right away, but you know, it indicates that they have to do something else. And they have tricks for dealing with that by changing the mixture of the grout and injecting sand as one of the ingredients. And you know, they do this stuff every day, so they know how to be doing good production. You don't need groundwater flow or water in the well, but if you have it, it can be beneficial and allow the design to include less drilling. The calculations for that can be a little bit more complex. They're not normally done on a residential installation, but on a commercial installation, especially a larger one where there's an array of borings, the groundwater flow velocity and direction can matter a lot as to how that array is oriented, so that the groundwater is evecting away heat in the summertime and bringing in temperate groundwater during the winter. Something around 600 or 700 feet of drilling, and we would normally divide that into 2 borings because the pumping overhead is less if we go through 2 borings in parallel instead of one long boring in series. About 10% of the time. In new construction, when we're just working from plans, we will configure the design so that it is at the maximum infiltration rate that the code would allow, knowing that that's going to be tested and they're going to have to be at that point or better. In retrofit scenarios, we're in an incentive program that's a pilot program, so it wasn't on the summary list, that is designed to reduce the total energy use of homes and reward that. And so on our retrofit projects, we're going out and doing blower door tests and duct leakage tests and surveying all the insulation and then making recommendations for ways to tighten up the home. And that's in response to that additional incentive being available. I hope that the pilot is successful and that everyone starts doing it that way, because it's a better approach to a retrofit. But in new construction, we just sort of assume that it has to be at least this good You know, if it's not this good, you're not going to get an occupancy permit. And then, so that's what we target. If they're going to commit in writing to me that they're going to achieve that, then absolutely, I'd be happy to. There are two steps. We bring in a tight roll-off container. So that looks like any other roll-off container, but it's competent and it has no leaks. A special filter is put in that, and they start pumping the water and the sediment into that roll-off container. As that starts to fill up, we, if necessary, will have a separate storage tank, usually a 4,000 or 5,000 gallon vertical high-density polyethylene tank that we pump the filtered water into. And then that can be infiltrated over time or can be taken away by a vacuum truck. About 15 or 20% if the digging's easy. Yeah, vertical closed loop is about 15 or 20% more than horizontal if the digging is easy. If the digging's hard, that gap closes very rapidly.
Easy for you to ledge, right?
No, easy means that it's sandy, there's not bony excavation conditions, so we're not getting a lot of cobbles and boulders and things like that. Because then the excavation contractor, who normally would work for the general contractor, not us, but the excavation contractor then needs to deal with all that. And you can't cut a nice, pretty trench like we had in the slide. If there are very rocky conditions, there'll be a lot of collapse and all that. Relative to cost, these weren't my company's costs. These came, Abode got this information from the Clean Energy Center and average costs of ground source installs over the last several years. So they're the market averages that are presented. The difference could be how big the house is, how high the heating load is, also how complicated the ducting system is. We do projects that exceed $100,000, but we also do projects that have net costs in the 20s. So it's hard to evaluate the disconnect without knowing the specifics of the instances you've cited, but there is difference in pricing between installers, and there's difference in sizes of houses. People have different approaches to the sizing of the equipment and the amount of drilling that's done. So I hope that at least partially answers the question. I don't think it fully does. Vertical is, has a very reliable cost. So it's somewhat safe in a budgetary sense. Horizontal excavation, lots of people come to us and want to do a horizontal loop. They see a lot of that on the internet, because in other parts of the country, it's all that people do. But here, the digging can be harder. They might not have enough space. They could have already mature landscaping. It's like, you really want me to take down the Japanese cherry tree, and but so space is the most important thing. And then it can also help if there's excavation that's going to be happening for some other purpose, septic system or the foundation, and you're not paying to mobilize. You've already got the equipment there. That can be helpful. No, much more piping goes into the ground for a horizontal system. Well, let me do the math. If we're doing, okay, we have 1 minute until refreshments, so I'll finish this call. 600 feet of drilling is 1,200 feet of pipe, plus whatever the offset is into the house. An equivalent slinky system is going to be 2,400 square feet of pipe at least, plus the offset.
But your trench is,
Yeah.
so how many linear
100 feet by 3 for 1 ton of slinky is the usual rule of thumb without having thought about any of the geology or how deep it's going to go and that sort of thing. And there are two. One is if it's oversized, you've done that much more drilling or whatever technology used to put in the ground heat exchanger, so you've spent money at the initial stage. And then secondly, you're spinning then a larger compressor, so it takes more energy. It's better if it's variable speed. If it's variable speed, it helps a lot. But even then, those variable speed units can only modulate down to a certain point. The 5 or 6 ton size water furnace units, the forced air units at full throttle are about 2,000, 2,200 CFM. And they can modulate down to about 400 or 450 CFM. The smaller units can go closer to 300, and that minimum airflow affects how small the smallest zone can be without hearing airflow through the ducting. So being the right size is best. If you're going to be a little bit big, being variable speed helps mitigate that quite a bit. A typical vertical well will generate like 5 to 8 cubic yards of material. And so the volume's not all that consistent. It's really the makeup, because it's made up of fine gravel, sand, and then silt-sized material, so it's pretty mucky and it's slow to dry out. When the drilling happens, the drill rig uses a pneumatic hammer in its process, and each stroke of that hammer releases a little bit of water, a little bit of air. And in the column of water of the well, that starts to rise, and that's called an airlift pump. And it'll continually remove water from the well because of the drilling process. So with closed loop systems, we really would love to have, hit the unfortunate dry conditions that someone would have if they had a failed water supply or irrigation well. If we hit conditions that would give somebody 100 gallons a minute, then that water has to be contained, managed. It can make things messier because there's just that much more mud when you're dumping thousands of gallons of water on the, and trying to infiltrate it. We will sometimes have to bring in a storage tank or something to control it, especially in an urban area. Thank you very much for your attention.